In 1995, the first planet outside our solar system was discovered. Since then, with improved techniques and tools, over 5,000 exoplanets have been confirmed, and another 10,000 candidates are awaiting confirmation. With some of those exoplanets, astronomers can actually study their atmospheres and search for signs of life. Learn more about the search for life outside the solar system and what exactly astronomers are looking for and why on this episode of Everything Everywhere Daily.
Spring is in full bloom at the Home Depot, so what are you working on? How about a quick and stylish patio furniture update? Check out a variety of on-trend dining sets with plenty of space for entertaining. And what's outdoor dining without a shiny new grill? Find a wide selection of grills under $300, like the Next Grill 4-burner gas grill for only $229. Then add a little ambiance with string lights. Transform your space this spring with everything you need from the Home Depot.
Don't miss your chance to spring into deals at Lowe's. Right now, get a free 60-volt Toro battery when you purchase a select 60-volt Toro electric mower. Plus, buy 3 19.3-ounce vegetable and herb Bonnie plants for just $10. It's time to give your yard a grow-up. Lowe's. We help. You save. Valid through 4/23. Selection varies by location. While supplies last. Discount taken at time of purchase. Actual plant size and selection varies by location. Excludes Alaska and Hawaii.
In previous episodes, I covered the search for life within our solar system. In 1976, for example, the Viking landers landed on Mars. They ran tests to determine if there were life forms in the soil. The results were ambiguous, and the tests have been debated ever since. If we wanted to search for even simple microbial life elsewhere in the solar system, we could send probes and landers to run tests or even return samples to Earth. The process would take years and might cost hundreds of millions of dollars, but it would be doable. We have a pretty good track record with interplanetary probes when we have the will and budget to launch something. Searching for life in the solar system, whether it's on Mars or the moons of Jupiter, is within the realm of the possible. In this episode, I want to focus on something else: life outside the solar system. Searching for life outside the solar system is a totally different problem. We can't send probes to other star systems, at least not with our current technology. The furthest we have ever sent a probe is Voyager 1. It was launched in 1977 and is approximately 167 astronomical units from the Sun, or 15,523,620,000 miles, or about 25 billion kilometers as of the time of this recording. Assuming that Voyager 1 was pointed at the nearest star to the Sun, that being Proxima Centauri, it would take another 75,000 years to get there. So assuming we were to ever send probes to other stars to search for life, it would require a whole slew of technologies that we have yet to develop. Because of these vast distances, the search for life outside our solar system requires a host of different techniques than the search for life inside our solar system. The first exoplanets were discovered in the 1990s by detecting wobbles and small dimming of a star's light when a planet passed in front of it. This technique couldn't tell us much about an exoplanet other than its mass and its orbit. But this information wasn't useless. If a planet were too close to its star, we could calculate its approximate surface temperature. If it was too hot, then nothing could certainly live there. Likewise, if it were too far away, it would be frozen and nothing could probably live. All of these early planets that were discovered were massive, and indeed the only way they could have been observed is if they were massive, else they couldn't have affected their sun enough for us to notice. However, techniques improved, mostly through the creation of more powerful telescopes such as the James Webb. Now it's possible to observe the light in the atmospheres of exoplanets. Astronomers analyze the atmospheres of exoplanets primarily through a technique known as spectroscopy, using space and ground-based telescopes to study the way light interacts with a planet's atmosphere. The fundamental principle behind this method lies in the fact that molecules in an atmosphere absorb and emit light at specific wavelengths, creating spectral signatures that can be detected and analyzed. One of the most effective methods is transit spectroscopy. This occurs when an exoplanet passes in front of its host star from our point of view, a phenomenon known as transit. During a transit, a small fraction of the starlight filters through the thin upper layers of the planet's atmosphere before reaching the Earth. Molecules and atoms in the atmosphere absorb particular wavelengths of the star's light, imprinting absorption lines onto the star's spectrum. By comparing the spectrum of the star during a transit to the spectrum when the planet is not in front of it, astronomers can isolate the spectral features caused by the planet's atmosphere. This allows them to infer which gases are present. This is a much more sophisticated version of how exoplanets were originally discovered. At first, they just measured the amount of light that was dimmed. Now they can observe what the light is actually made of. A similar technique, called emission or secondary eclipse spectroscopy, is used when the planet passes behind the star. By observing the combined light of the star and the planet just before the eclipse and comparing it to the light of the star alone during the eclipse, astronomers can subtract the starlight and obtain the planet's thermal emission or reflected light spectrum. This method provides insight into the temperature structure and composition of the planet's dayside atmosphere. Yet another powerful approach is direct imaging spectroscopy, although it's much more difficult and only possible for a few exoplanets that are far from their stars and relatively young and hot. In this technique, astronomers block the bright light of the host star using a coronagraph or star shade and directly capture the much fainter light from the planet. All of these methods rely on the absorption and emission characteristics of specific molecules that leave distinct imprints on the spectrum. By comparing observed spectra to models of atmospheric chemistry, scientists can deduce not only which molecules are present, but also their relative abundances, temperature gradients, and pressure profiles. These observations are extraordinarily challenging. The signals from an exoplanet's atmosphere are often less than 1 part in 10,000 of a host star's light. Instruments must be extremely sensitive and carefully calibrated, and astronomers must correct for interference from the Earth's atmosphere and other sources of noise. So that's how astronomers are getting their data. It's a very sophisticated way of analyzing light. So the next question is, what exactly are they looking for? How can you tell if there's life on another planet by just analyzing the contents of the atmosphere? There are several biosignatures that are looked for that might be indicative of the presence of life. And I should note that everything they're looking for is based on what we know of life on Earth. We have one and only one data point. We know that carbon DNA-based life does exceedingly well on our planet, but we don't know if some other form of life might exist somewhere else. One of the biggest signs of life would be the presence of oxygen. On Earth, the majority of oxygen is produced by photosynthetic organisms, such as plants, algae, and cyanobacteria. These organisms take in carbon dioxide and water, and using sunlight as energy, convert them into sugars and release oxygen as a byproduct. This process is the dominant source of free oxygen in the Earth's atmosphere, which is composed of about 21% oxygen molecules. Over time, oxygen will bind with almost every non-oxidized exposed surface. As new rock is slowly formed over geologic time, it will become oxidized. If all life on Earth were to disappear tomorrow, about 99% of the oxygen in the atmosphere would be gone in about 2 million years. And that isn't very long in the length of the cosmos. Moreover, if life had never evolved, there would never have been much oxygen in the atmosphere. So the presence of oxygen in an exoplanet would be considered a huge biomarker. Now, that being said, oxygen is not a foolproof biosignature. There are known abiotic or non-biological processes that can produce oxygen under the right conditions. For example, ultraviolet radiation from a star can break apart water molecules in a planet's upper atmosphere through a process called photodisassociation, releasing hydrogen and oxygen. If the hydrogen escapes into space, which is more likely on smaller planets with weak gravity, the oxygen can be left behind, potentially accumulating in the atmosphere. Certain geological and chemical processes can also, in theory, lead to an oxygen buildup. Methane is considered a potential biomarker in the study of exoplanets because a significant portion of atmospheric methane on Earth is produced by biological processes. Specifically, it's generated by methogenic microorganisms, which thrive in oxygen-poor environments such as wetlands, animal guts, and in deep-sea hydrothermal vents. These microbes break down organic material anaerobically and release methane as a metabolic byproduct. However, methane is not unambiguously biological, which complicates its interpretation as a biosignature. Several known abiotic or non-biological processes can also produce methane. But if methane is found in a state of chemical disequilibrium, for example, coexisting with oxygen, its significance as a biomarker increases dramatically. On Earth, oxygen and methane should rapidly react with each other and disappear. So the sustained presence together implies continual replenishment from opposing sources, typically biological ones. There are other biomarkers that might be even better, which brings me to the impetus for doing this episode. Just a few days before this episode aired, researchers announced that they had found evidence of something very interesting in the exoplanet K2-18b. K2-18b orbits the star K2-18, which is found in the region of the constellation Leo and is about 120 light-years from Earth. It was discovered in 2015 by the Kepler Space Telescope. It's about 2.6 times the radius of the Earth and is located in the habitable zone of the star. It gets about the same level of light as the Earth gets from the Sun. In 2019, water was discovered in its atmosphere, which is, of course, a very promising biomarker. In 2023, carbon dioxide and methane were both found in the planet's atmosphere. Again, both are potential biosignatures, and both can also be found on lifeless planets in our solar system. However, the 2025 announcement might be the biggest one yet, not just for K2-18b, but for any exoplanet yet discovered. They found evidence of dimethyl sulfide. Why does dimethyl sulfide matter? Dimethyl sulfide is known on Earth to be exclusively produced by biological processes, especially phytoplankton in oceans. Its potential detection is not conclusive evidence of life, but it's a biochemical whiff that piques scientific interest because no well-known non-biological processes produce large quantities of dimethyl sulfide. The specific structure of dimethyl sulfide, a molecule with two methyl groups bonded to a sulfur atom, is not something that commonly arises from thermodynamically favored reactions in high-pressure or high-temperature environments without biological catalysts. In laboratory settings, it's hard to make dimethyl sulfide without using organic precursors. Again, just as we don't know if biological processes on other planets would behave the same as on Earth, there might be geological processes on other planets that might be different as well, and they might produce dimethyl sulfide. That being said, it isn't just the dimethyl sulfide alone that has researchers excited. It's the fact that the planet is in the habitable zone, it has water and methane in its atmosphere, and it has dimethyl sulfide. Those are 4 important bingo boxes for life that have all been checked off. This is an exciting prospect, but there's still a lot we don't know. Researchers will probably be debating K2-18b for years. Now that it's a subject of controversy, there'll probably be more observations of the planet in an attempt to gather more data. Given the many thousands of exoplanets which have already been discovered, and the tens to hundreds of thousands which have yet to be discovered, K2-18b might just be the first of many potential exoplanets which harbor life. If someday in the distant future we develop technology that can visit solar systems light years from Earth, it might be that the destinations we select to visit might be determined with data that was first discovered during our lifetimes in the early 21st century. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Austin Oken and Cameron Kiefer. Today's review comes from listener D. Dean over on Apple Podcasts in the United States. They write, one of my top 2 podcasts. What a coincidence. Just yesterday, I'd been doing research about palladium, especially for jewelry. So when I clicked on Everything Everywhere Daily for my daily dose of knowledge and insight this morning, I was pleasantly surprised. Episode 1742 was all about palladium, platinum, and rhodium. I thoroughly enjoyed listening to Gary give me unique info about each of these metals and their benefits. Thank you, Gary, for your range of topics, thorough research, and the digestible nuggets you give us about everything, everywhere. You've helped me to remain a lifelong learner. Blessings. Well, thanks, D. Dean. This is another one of those everything everywhere coincidences. Given enough episodes and enough people listening, they should pop up pretty much all the time. Remember, if you leave a review or send me a boostagram, you too can have it right on the show.